Hello and welcome back for one more example. This time we are going to look at h of s is equal to 30 times s plus 10 divided by s squared plus 3s plus 50. So we have a set of complex poles in the denominator. So what we're going to do in order to do this one is, again, we're going to follow those same steps. First step, find the transfer function. In this case, it's given. Second step, we want to rewrite it in the standard form, sketch the magnitude, asymptotes, add the correction points, sum the lines, then connect the dots. Repeat for the angle. Let's start off. We have this form. We want to put it in the standard form. Well, we know for a first order term, such as the s plus 10, we want to make it an s divided by 10 plus 1. But what do we need to do for a quadratic form? For an s squared plus 3s plus 10. Let's go again to our rules for making Bode plots. If you look at this, we have an underdamped poles section, and it shows it in the standard form where we want it to be s squared, quantity, s divided by omega squared, omega naught squared, plus 2 zeta times s divided by omega naught plus 1. So the key thing is still keeping this 1 in the constant spot. So let's go back and put it into the standard form. We're going to start off, we're going to say that h of s is going to be equal to, we have a constant of 30 that we're going to keep out front, but we're also going to pull out the 10 from the numerator. Then in the denominator, we're going to pull out the 50. So we have a 30, a 10, and a 50 out front for the constants. And what that's going to do is that's going to give us the correct form of s divided by 10 plus 1 in the numerator divided by s squared divided by 50 plus 3 divided by 50 s plus 1. Okay, so this is the correct form that we wanted in, but let's go ahead and take it a little bit further. We can do a couple of things as we're dealing with this. First thing we can do is we can form up this constant. So we can go ahead and say that this is going to be equal to 6 times s divided by 10 plus 1 divided by, let's go ahead on this denominator term, and if we go and look at our Bode plot rules again, we can see what we want it to be in the form of. We want it to be in the form of quantity s divided by omega naught squared. So we need to put it into that form, s divided by omega naught squared. So, or s divided by omega naught quantity squared. So that would mean that we're going to have an s divided by square root of 50 quantity squared. All right, so we get a very important piece of information from this. We get that omega naught for this pole is going to be square root of 50. We also get the constant term. So let's write the constant term up here at the top and just note it down. So our constant is going to be equal to 20 log of the absolute value of 6, which that one is going to actually be equal to 16 dB. And we also know that for the pole, we have omega naught is going to be equal to the square root of 50. So now let's write the second term. The second term that we need to write is going to be in the form of 2 zeta s divided by omega naught. So if we want to go ahead and write this, plus 2 zeta s divided by the square root of 50 plus 1. Plus 1, okay. So now we know that 2 zeta s divided by 50 is going to equal to 3 divided by 50. So let's write that out. We also know for this pole that we're going to have 2 zeta divided by the square root of 50 is going to be equal to 3 divided by 50. Let me minimize this just a bit. Okay, so now if we're going to try to solve this, we need to solve for zeta. So therefore, zeta is going to be equal to the square root of 50 divided by 50 times 3 divided by 2. And if we calculate all of that out, we are going to get that zeta is going to be equal to, I have it written down here somewhere. Zeta is going to be equal to 0.21. And so these are the terms that we need. We need zeta is equal to 0.21. We need that omega naught is equal to the square root of 50, which is also equal to the square root of 50 is going to be equal to 7.07. And we need that the constant is going to be 16 dBs. So these are the values that we need to know in order to go to the next slide and do the Bode plot. So let's go ahead and do that. All right, so now we need to do our plotting. We need to have 3 straight line asymptotes that we're going to sketch. We need to do the constant, we need to do the 0, and we need to do the pole. Well, this pair of poles that's in the denominator. We're going to draw those as one asymptote. So let's go ahead and we're going to start with the asymptote, the constant, which was at a constant value of 6. That gives us a dBs of 16. So here's 20. Let's see, 5, 10, 15, a little bit above right there. And we're going to give us a dotted line at a constant value of 16 all the way across the board. And so this is our constant. All right, now that we have our constant, that's one of the 3 straight line asymptotes that we need to put onto the plot at 16. The next one that we are going to do, let's go to the easiest one next. We're going to do the 0 at 10. We should be getting things down now. So we're going to go along at 0 dBs until we get to that turning point, that knee, which is at 10. 10 to the 1 is 10. And so that means right here is where we're going to turn the slope up. It's going to go at 20 dBs per decade. So we're going to go over 1 decade, which is 10 squared, and we're going to go up to 20 dBs. So that's going to be right there. And we're going to draw a straight line, as straight as I can between those two. Let's see if I can actually get something close to straight. So that's going to go up that way. And then this before that is going to be at 0 dBs. So we're starting off, it's going to go along at 0 dBs until it gets to that omega value. At that omega value, the ratio of S divided by 10 is going to take over. And that's when it turns up and it goes up at 20 dBs per decade. So now let's go back and look at our rules for making a Bode plot again. We have an underdamped pole in the denominator. So low frequency asymptote at 0 dBs. All right, hey, we're starting off easy because that's what we've been doing for all the other ones. High frequency asymptote at -40 dBs per decade. This kind of makes sense because what we're doing is looking at that term that's the S divided by omega squared. When we do 20 log of that term, the squared comes out in front, and that goes from 20 to 40. So we're going down at negative 40 dBs per decade now instead of negative 20 because that squared term, that's the S divided by omega naught squared. But we're still turning down at omega naught. So connect the asymptote lines at omega naught and then draw the peak at frequency omega naught with amplitude. And here's an equation that you can use. The shape of the peak is dependent upon the zeta value. The zeta value is related to the poles and zeros of this. But right now, we're not going to worry about where zeta comes from. We're just going to look at this and plug it into that equation. Or instead of plugging it into that equation, we can actually go to the zeta correction rules. And we can look at our zeta value and find an approximation fit from this line. This is the other handout that we had. But for now, let's finish doing the straight line approximation. This is pretty easy because now all we need to do is look at the first term, the S squared divided by omega naught squared, square root of 50. Well, again, when we did that, the omega naught, that is 7. So 10 to the 1 is 10. And now we're going to go back 9, 8, 7. So 7 is just a little bit below 10. And so it's going to be right in there because this is a logarithmic scale. So here's 1, 2, 3, 4, 5, 6, 7. You can see how they all start to get bunched up around 10. So you gotta count back on the dotted lines. But now we're going to go down by 40 dBs per decade. And on this plot, I have it going out to, I don't have it going out quite far enough, but we can see that if it was going to be 20 dBs per decade, it would be here. It needs to be double that slope. So we're going to pull it back into the middle, and 40 dBs per decade, we're just going to eyeball it. It's going to be about there. We're going to double it so it would come out to there. So if we start here now at 7, we're going to turn down and we're going to go down at 40 dBs per decade. So here is our 0 at 20 dBs per decade. Oops, I'm writing all up in the words. Sorry. So here is our 0, and that 0 is located at 20 dBs per decade, at 20 dBs per decade. And down here at the bottom is our pole, and this pole is going to be located at 7, going negative 40 dBs per decade. Because the S squared term is going to dominate. The second term, and I actually have a typo, this shouldn't be 50, this should be 1. The second term is going to control the amount of overshoot or undershoot, the correction point right here. The zeta controls the correction point. And then the third term is what really dictates when it turns on. That's that constant that's creating the 0 dB up until the knee in the plot. Okay, so now what we need to go and do, we need to go and look at the correction points. So for a first order like this 0, we know it's 3 dBs. So we are going to put a point at 3 dBs right there. Easy. For the other one, for the quadratic term, we are going to go and look at the zeta correction chart. Now remember, our zeta was a 0.2. And so if we look at the zeta is equal to 0.2, that's the second line down. That's that yellow line. And so you can see, if we're looking at this as the straight line approximations, you can see how it's going straight, and you can see the negative 40 dB per decade. So our correction point is actually above the knee, not below it. If zeta is equal to 0.7, for instance, it would be below it. But because we're at a 0.2, our correction point is actually going to be above the line. So let's go back and put that correction point 0.2. It looks like our correction point, and we could get an exact value if we wanted to plug it into the equation that is here. We could plug it into this equation and get an exact value. But if I look at this, it looks to me like it's about 8. So let's go back here, and we're going to put in a correction point at 8. Well, this is a correction point at 3. Here's our 5. Here's our dBs, 10 dBs. So we're going to come down just a couple off the 10 dBs, and we're going to put a correction point right about there. Now we need to sum everything together. All right, this is where it gets a little bit tricky because we have these straight line approximations and we have the correction points. And so we need to transpose these correction points up and we need to sum those into the equation. So let's start summing. We come all the way back here at the beginning of time. We have our constant plus 0. So that just leaves our constant. So we're going to travel along the constant. Let me grab I'm going to try the pink marker and see if the pink marker shows up this time. Does that show up? Yeah, it looks purplish, but that's okay. So we're going to go along here, and we're going to go along here until we get to the first point of action. And when we get to this first point of action, we now need to sum all these things together. So we can just sum, and we can take this correction point and sum it together with 16, which was our constant. And so that's 8. So that gives us a 24 where this is going to be. And so that's somewhere right around in there. Oh, that's actually above 25. So that's right about in there. 24, that correction point is at 24. Okay. Now we get the slope kicking in of the poles. Negative 40 dBs per decade. So we're going to start to drop down at this slope, but we're only going to drop down at that slope until this 0 kicks in. So we're going to go for only 3 rad per second. We're going to go from 7 to 10 at negative 40, and then we're going to have a negative 40 plus a 20. So we're going to drop to a negative 20 dB per decade. So we're going to do that straight line asymptote right now. And so this is going to go down at the same slope as this line below us. So I'm going to try to copy that. And it gets to about there. Okay, somewhere in there. Now we need to add in the positive 20 slope and this correction point. So we need to put this correction point 3 dBs above where the straight line approximation is at. So here's this correction point. Here's where our line ended. So we're going to add 3 dBs above there. And that actually puts that correction point right about there. And that's what we're going to do with the connect the dots. We're going to first go through this top one, then go through this one, and then we're going to come and approach the straight line asymptote. So now we have a positive 20 dBs per decade. We have a negative 40. Positive 20 minus 40 gives us a minus 20 dBs per decade. So we can actually look at where this is at right now. And we are sitting at about just a little bit over 10 on the magnitude scale. And so we know that 1 decade later, which this one turned on at 10. So at 100, we're going to be 20 below this current point. And so if we go 20 below this point, that is going to be 5, 10, 15, 20, and a little bit up. And so we're going to come over and we're going to put a point right about here is where we're going to end up because we're a little bit above the 10 line right now. And so now we can draw a straight line from there to there. It's going to be about something like that. Again, this is an approximation, so we're going to try to get as close as we possibly can, but we might not be perfect. When we have our straight line approximation, we have our correction points. And now the finale, we're going to sum all, after we've summed all these together, we're going to connect the dots. I have this other marker that I found that you're supposed to shake. So let's see if this marker gives us a good representation of what this line looks like. So we're going to start off and it's going to be still the same thing. So all these are the same, but now on our straight line or our smooth line approximation, we're going to jump up and go through that data point or that correction point. We're going to go through this correction point, and then we're going to come down and level off as we go on down the way. And so that actually looks pretty good. You can see that green line, that smooth line, pretty good. We're sitting at a constant pass band for low frequencies. We get to the cutoff frequency and we've got a little bit of Gibbs going on. We're having a little bit of a peak going on here. So it's actually going to amplify these frequencies just a bit, but that gives us a sharper cutoff. So a lot of the times when you are doing a real filter implementation, that's what you've got to consider. Do you want to bump up just a bit? But if you bump up, that gives you a sharper downside. So we're going to have a little bit where these frequencies are going to be amplified, but then it cuts off real sharp to get down to this 3 dB point, get down to the 3 dB point, and you can see the slope of this line to get to that half power point is a lot more dramatic than it was on the other filters that we were designing. And then it fades off at a negative 20 dB per decade for the rest of it. So that is how you do the magnitude approximation Bode plot with a quadratic term in the denominator. The last thing that we need to do is repeat this process for the angle measurement. So we're going to start with our standard form. We're going to sketch the straight line angle approximations. We're going to add in the correction points. We're going to sum the lines, and we're going to connect the dots to make our smooth line representation. So again, we're going to start out by looking at our Bode rule sheet. We've already done it for the constant. We know that if it is a positive number, it's 0 degrees. If it's a negative number, it's a negative 180. We know how to do a real pole and a real zero. In order to do this, we go 1 decade above, 1 decade below. Those are both at 0 and either positive or negative 90, depending on whether it's a pole or a zero. And then we connect the straight line through the two. What's new is now we're going to look at the underdamped poles or the underdamped zeros. We have an underdamped pole. So for the phase, we're going to have a low frequency asymptote at 0 degrees, high frequency asymptote at negative 180. Again, this makes sense because we had a negative 90 before, but we have that S squared term. So it's going to double the phase. Connect with a straight line from negative 10 to the zeta below up to 10 to the zeta above. So we're no longer going 1 decade above and 1 decade below. We're actually going to look at a different zeta chart. And so if we have this straight line approximation from 1 decade below to 1 decade above, just like it shows here, here's 1 decade below the omega naught, and all the way on this other side is 1 decade above. We can see that the zetas change the reach of the phase distortion, and they also make it more of a steep phase distortion around omega naught. All right, so let's start off with the ones that we know and go from there. We're going to start out with an angle correction, and so we have a constant that is a positive. Given that positive value of 6, we know that that's going to be a 0 degrees. And then from that 0 degrees, the next thing we're going to do is we're going to look at the S divided by 10 plus 1, 0 term. Because it is a 0, let's refresh our memory. Because it is a real 0, we're going to go to positive 90. Positive 90 at 1 decade above. So 10 to the 1 is 10. 1 decade above that is 10 to the 2. And we're going to go up to positive 90. And so that is this point right here. We're going to go right there. And then 1 decade below is going to put us right here. We're going to go from there. And so that's the straight line that we need to make. And that's longer than my ruler. So I'm going to try to make a straight line. Not bad. Okay, so there's a straight line transition from 1 decade below to 1 decade above. And it is transitioning a total of 90 degrees. Now let's go to the final term. We're going to go ahead and do exactly what they did on this zeta correction chart. On this zeta correction chart, they still did this straight line approximation from 1 decade above to 1 decade below. But then with the zeta correction, you can see how far the reach actually goes out. So we're still going to do a straight line from 0 to negative 180, 1 decade below. Again, omega naught is the square root of 50. Square root of 50 is approximately 7. So 10, 9, 8, 7 is somewhere right in here. And so 1 decade below is where we're going to start at the 0. 1 decade above 10, 9, 8. Let's see. Here is 10. 11, 12, 13, 14, 15, 16, 17. Yeah, I didn't know if this plot actually had 10 tick marks in it. It should. And then we're going to come along here at the negative 180 line. And the negative 180 line is right about here where we're going to connect them together. So right here. Okay. That's where we're going to go. So now we're going to draw this straight line approximation as straight as I can make it through there. And then we're going to go 0 off of there. Now we go and look at the zeta chart, or we can use the equation. This is 10 to the negative zeta. Well, zeta in our case is 0.2. So we could do 10 to the negative 0.2, or we could go and approximate it from this chart, looking at the zeta of 0.2 in order to get the pseudo-randomized shape. And we can see that in this shape, it is looking like it is about at negative 20 degrees when we are 1, 2, 3, 4 degrees below it. And so I'm just going to go and I'm going to put a data point on here that looks about like what that was saying. And so that looked like it was going to be around there and around there. And so I'm going to copy the shape from that plot on the last page. That's all I'm doing. I'm eyeballing it. I'm copying that shape in order to put a couple of correction points. Now, remember, the phase isn't as important as the magnitude. Usually you want your magnitude to be right on, and then the phase, you have to deal with. This is kind of like how you pay the piper. There are some applications where you want a really good phase, but usually this is what you have to sacrifice. All right, so now let's sum them together. We have done our straight line asymptotes for each one of the terms. We have done our correction points. Now we're going to sum the lines together. And when we sum them together, we can see we start off everything as is at 0 degrees. And then the first point of action is this denominator term, and it's going to go down. So we're going to go along here, down just a bit. Oops, that was way too far down. Talk about dramatic. We're going to drop down to there. Now, what we need to notice is that as we drop down, we now have this angle here on this straight line approximation, and we have this angle here. Well, they sum together and they come out to still a negative angle, right? Because this one over a decade is going to 90. This one's going to 180. So we are still going to have a sum resultant that is going extremely that's going negative. But it's not going to be as dramatic as the other plot might show. Okay, so at this point, we're going to go down negative, and so we're going to not go quite as dramatic with our slope. And we're going to go to here. And this is where this one kicks off. And so at this point, we're going to have just a little upward tick, and then we're going to go straight across from there. Now, the zeta correction is really what comes into play here, because we need to move these two zeta correction dots up on top of this. And so that's going to put one of the zeta correction dots here. That's going to put another zeta correction dot right here. And again, I'm eyeballing it. So that's what it's going to go through. So now when we sum all these things together and put our final smooth line approximation on here, I'm looking at this point. That's the correction point that I'm going to go through, is this one right here. So I'm going to go along the asymptotes, but I'm not going to go, I'm going to deviate off. Now I have to go all the way down to this one. So we're going from this high one all the way down here, and it's going to be a dramatic phase transition. And then once we hit here, we are going to go back in towards this asymptote, and it's going to be out like that. So it's going to be some transitions such as that, where this is going to dramatically drop down and then continue on its way. Okay, so that is an example. We have so far went over 3 examples. One of them was extremely simple. One of them had multiple poles and multiple zeros. And this third example had both poles. It had a 0, and then it had a complex pole in the denominator that we use the zeta correction for. And so that's it for these. If you need more resources, there are some video lectures by Professor Lanterman that goes over the transfer function Bode plots also, but not in detail of how to hand draw them, as I have been going over in this video series. So please post any questions that you have. Let me know, and have a good break.